All right, ladies and gentlemen, so as we go through this lesson here, it's going to be a little bit different because this is a very activity-driven lesson. So you will, at the very least, you'll pause for a long period and then come back to the video as you work your own way through this activity. Because of that, we're going to be going over this lesson in class. Okay, even so, you can get a little bit out of this video just from some definitions at the beginning before we pause and we need to go over that activity as a group. So we start off here with just a few definitions. Like I said, we are hopefully very comfortable with how to recognize a polynomial function, in particular from an equation or from a table of values at this point. Now, a polynomial function, as it's shown, and just a quick review, it's a sum or a difference of power functions. Again, if you're not familiar with power functions, I want you to go back and check out the 3.1 video. Now we're going to call, and this is some new terminology, a leading coefficient is what we call the coefficient. Remember, the coefficient is the number that multiplies by your power. Right, in your power function, it's the number that comes before your power. So the leading coefficient of a polynomial is the coefficient of the term with the highest exponent. Okay, so for example, we have two polynomial functions written up here. Let's take a look at the first one. The first one, we're trying to find the term with the highest exponent. This is written in almost a standard form here, as you may have seen polynomial functions before. So your term with the highest exponent, that happens to be the one that's written first. So that exponent is 9, right? So the degree of this polynomial will be 9. The leading coefficient of our first polynomial here, the leading coefficient would be the 6, and that's the 6 right here. Okay, now for our second polynomial here, we have only 3 terms, right? We have negative 14x cubed, we have 11x to the power of 5, we have 64x. Now of those, it's no longer written in cascading order of with the highest exponent written first. So we need to identify that in here. Our highest exponent is 5. So the degree of this polynomial is 5. The leading coefficient is 11 right here. That is the coefficient attached to the term with the highest exponent. Okay, so our leading coefficient with the second one is 11. Now our next definition. Okay, now we're thinking a little more graphically. A polynomial often has maximums or minimums. Now, an absolute maximum or an absolute minimum is the greatest if it's a maximum or least if it's a minimum value of a function. So if it's the highest or lowest value of a function, that's the y value we're considering, right, from the function, because your function is f at x, right? So it's the greatest or lowest y value for all values in its domain. And you have seen maximums and minimums given in that situation before. For example, a nice and simple scenario would be with a quadratic function like this. We would see a maximum occurring right here. We would call that an absolute maximum, because that is the highest value, the highest y value on this function, no matter what. No matter if you check all of the possible y values, if you check everywhere, every x value, there is no y value with a higher value. So this would be an absolute maximum. Okay, now we can also have, with a polynomial function, we can have a local maximum or minimum. And that is a local maximum or minimum is the greatest or least value of a function for just a part of its domain. Okay, so a part of its domain, well, hang on, that might happen all over the place. It doesn't really, right? So if we have, say, a point right here, this would have, if we're looking at this is a polynomial function, this would have a value right at the bottom here that is lower than any other value beside it. If I zoom in, no matter how much I zoom in, this point right at the vertex here is lower than all of the other values beside it, but it's not lower than the function over here. So we would call this one just a local. In this case, it's a minimum. Okay, that also can be in terms of a maximum as well. Now, next, what I want you to do. So this is the first activity here, and this is a pretty elaborate activity. So you will be pausing the video in just a moment. But before you start this activity, what I want you to do, if you have any highlighters near you, I want you to go grab two different colors of highlighters. Okay, once you've done that, we're going to mark the polynomials that have even degrees separately from those that have odd degrees. Remember, you should be familiar with how to recognize an even degree versus an odd degree. I'm going to go with a blue highlighter for those with odd degrees. So let's say right here I have an odd degree polynomial. If you'd like, you can put it right across the entire thing. That might mess you up a little bit. Maybe put a highlighted square around it. Okay, so your odd degree polynomials with a square, just so we can easily identify, if we back up, we can easily identify the kinds of polynomials that we're working with. Okay, and then use your other highlighter. Really make it obvious here. We'll use green for even degreed polynomials. They should look something like this. And then you can use, we're going to categorize these green ones together, these blue ones together, and try and find some patterns that go through them. I will ask you, at this point, you can pause the video. I want you to try and analyze each of these 9 functions that are graphed for you to try and answer all of these questions. The first group of questions is for odd degree polynomials. The second group of questions is for even degree polynomials down here. Okay, now what I want you to do, I want you to try that out and then pause the video and come back to us here. Good, so now that you're back with us, you will be able to check afterwards. Once you're finished those, you'll be able to check your answers. I will upload the answers for the conclusions there on the Brightspace Classroom. But we want to jump into some new definitions. So let's take a look here. So you may have noticed, and again, this is assuming that you have gone through with the previous activity. You may have noticed that a polynomial, if we say it has degree n, then the maximum number of turning points the polynomial can have is is that degree minus 1. So in this case, if our degree is n, then the maximum number of turning points is n minus 1. Okay, now an inflection point, it can occur in some of our polynomial functions. An inflection point occurs where a curve changes in concavity, and that might be a little bit of a new concept for you. So that is, it's changing from concave up to concave down. So let's say we're working with a cubic function here. If I have a cubic function that looks like so, first of all, you should already be able to tell me some stuff about it. You should be able to tell me how many turning points there are, the n behaviors. You should be able to tell me the sign of the leading coefficient and a little bit more. But at this point, we want to focus on where it changes in concavity and what that really means. So what that means is we're either working with and you may remember working in science with concave and convex materials, but we're always going to write that to refer to them in terms of being concave up or concave down. So concave means the part of the curve that creates a bit of a cave. Okay, so let's say right here, and you know what? Let's split off our function right here. I'll tell you the point of inflection is right here, the inflection point. Inflection point, and you'll see what that means, why it's changing in concavity. Well, a change in concavity, so if it's concave up, then we'll say a curve has this general shape. Okay, something that's concave up would be like a spoon that's holding your nice hot soup. Okay, your spoon can hold things if it's concave up, but as soon as your spoon is concave down, let's here in green we have a concave down spoon, something like this. Someone's turned the spoon upside down. It no longer is holding the soup. It's now pouring the soup out. Hopefully no one's getting burned over there. But either way, what we have here, we have something that's concave down. It cannot hold anything. Okay, like an umbrella, cannot hold. An umbrella is concave down. It protects from the outside, right? Nothing collects. No rainwater collects when you use an umbrella because it hits the umbrella and it bounces right off. It would not happen if you turned your umbrella upside down, which I suspect some of you may have done when you were younger. If you turn your umbrella upside down, then you're trying to collect all of the rainwater that you can. So you might notice that different parts of our curve here, and allow me just to redraw this curve just a tiny bit. Perfect, there we are. And I'm just going to change in color, there we are. You might notice that one part of this curve is concave up. So if it were raining across the entire curve here, you would see that rainwater would collect over here. That's because it's concave up. Okay, but rainwater would not be collecting over here. It would just be bouncing off. Right? No rainwater is getting beneath our curve on the inside here, so this is concave down. So the point of inflection is the location on our function where it changes from being concave down to concave up. Or a point of inflection will occur if our function is changing from concave up to concave down. It's just where our function changes in concavity. Okay, now that part might confuse you. We are looking a little bit deeper into our polynomial shapes than you have before, and if it confuses you, that's okay. We'll talk about it in class. Now, an inflection point. If we're going back to talking about the maximum number of turning points that a function can have, an inflection point is actually what happens if two turning points get too close to one another. Okay, so an inflection point can sorry, bear with me here. An inflection point can, if our slope comes to 0, so let's give ourselves another sketch here. This time it's going to be of our base quadratic function, which you have seen, or base cubic function, which you have seen before, something like this. Then we would have a point of inflection right here because it changes from concave down to concave up here. But you'll notice there is no local maximum or minimum because this function is increasing beforehand and it's increasing afterwards, so there's no turning point involved. Now if there's no turning point involved, we can still have an inflection point. That inflection point is happening right here, and that is where it's changing in concavity from upwards to downwards. And this inflection point, and these kind are going to be our main focus in here. An inflection point here is really what happens to a cubic function if it's two turning points, and that's a very terrible cubic function. If its two turning points get close enough together, so that here we could have two turning points here and here. If they get close enough to one another, like what's happening with the green function down there, then we're working with an inflection point, and it kind of represents, in this case, two turning points if the inflection point occurs where the slope, where the instantaneous rate of change equals to 0, okay, or approaches 0 down there. Now, what I will want you to do next is handle, probably using Desmos as your favorite graphing calculator. Again, you're going into your own activity. I want you to try it out. You're just going to follow the instructions there and perhaps come to a conclusion about the symmetry, and that is even or odd symmetry. And if you don't remember what those are, then go back to section, I think it was 1.3, where we learned about those. Even or odd symmetry of these polynomials. And then from that point, let me see here. From that point, the rest of the examples, we'll do one more here in the video. So try this out. Pause the video, try it out, and then come back, please. Good, so you should be back with us. You've gone through that activity. I'm hoping you learned a little bit. We will, again, the conclusions will be posted on the Brightspace Classroom. So next we want to look at, and this is just our first example of the note here, we want to take a look at a graph of our polynomial, and I want you to come up with the degree of the function that's involved, the sign of the leading coefficient, all of these different characteristics you should be able to come up with based on the patterns that you have already found. So I will encourage you here, pause the video, try it out, see how many of these properties you can figure out from referring to earlier into this note to those patterns that you put together. Okay, so here, and again, I'll say pause the video, then come back right now. I'm about to go through the solutions. So the degree of our function, we know about the degree. We don't necessarily know the exact degree that we're working with. Okay, but what we do know that it's an even degree because the directions of these n behaviors, they're going in the same direction. They're the same, right? So here we would say, okay, well then it's going to be an even degree. Now, we also do know the minimum degree that we're working with here because we know the number of turning points at the very most is one less than the degree. Okay, well here I have only one turning point. It's at 327. But I also have a point of inflection, an inflection point right here. And an inflection point we know counts for 2 turning points. Okay, so an inflection here where the slope goes to 0, it counts for 2 turning points. So that is, we have 1 turning point here. We have 2 and 3, both in here. So the degree must be at least 4. Okay, so the degree must be greater than or equal to 4, and we know that it's an even number. That's how much we can tell about the degree. Okay, we're not able to determine exactly the degree we're working with, but we do know something about the degree. Now, the sign of the leading coefficient. Well, we know it's an even degree. We know that because our n behaviors are going in the same direction. Because this direction that the n behaviors are going, because our function is approaching negative infinity, as x approaches positive or negative infinity, then the sign of our leading coefficient is negative. Okay, our domain, nice and easy here. Just like all polynomial functions, our domain is x is an element of the reals. Our range here, because it's an even degree, our range will have a restriction. Okay, so our range here, y is an element of the reals such that y, and in this case we see our local maximum over here where y equals 27. So y must be less than or equal to 27. Now, local maximums or minimums. Okay, well, what I see over here, again, is is an inflection point. It's not a turning point. Because of that, it's not going to give us a local maximum or a minimum. Here we have a local maximum only at the one turning point. That's at 327. So we are going to have, at 327, every single turning point will give us a local maximum or a minimum. Now, only one of those could be an absolute maximum or a minimum. In this case, it is because our function never gets higher. The y value of our function never gets higher than 27. So our absolute maximum or minimum as well in the exact same spot, that's 327. Okay, now lastly, we want to look at intervals of increase and decrease. Well, we have worked, and we just touched on it when we learned about our intervals of increase and decrease. Our inflection point, our instantaneous rate of change equals 0. Okay, that is, our function is neither increasing nor decreasing right at that point. But our function is, if I remember how to determine if my function's increasing or decreasing. If you don't, again, that's section 1.3. We're looking from left to right on our function. We can see that it's increasing from negative infinity to 0. So it's increasing from negative infinity to 0. Union with it's also increasing along here from 0 to 3. And then our interval of decrease would be from 3 to infinity. Okay, again, that's section 1.3. And lastly, our n behaviors. I threw this one in here because judging on the first assessments, we can use some extra practice with our n behaviors. Here they're nice and simple. So as x approaches, and you know what, I'll give you a little bit of a shorthand for how we can write this and save ourselves some time because, again, mathematicians are lazy. As x approaches positive or negative infinity, y approaches negative infinity. Okay, now we've gone through the logic involved here. You have discovered some patterns already. You should be able to handle trying to draw some conclusions from this next graph here. So pause the video, try it out, please. Again, these solutions will be posted on the classroom afterwards. Next, I do want to get to our second example here, and this is we're handling an equation, and we're trying to determine some things from this equation. Okay, so it's a polynomial function, we know that. What can we determine about this? We know the degree is 3. We know the leading coefficient is 4. We want to try and find the end behavior, so let's write that out. So our degree equals 3, our leading coefficient equals 4. Okay, so the end behaviors of the function. Well, if our degree is 3, then our end behaviors must be going in opposite directions. Right? So since our degree is odd, now if you haven't seen it before, the upside down therefore sign, that's 3 dots here, that's what it looks like. It means since. So since our degree is odd and our leading coefficient equals 4, our leading coefficient is greater than 0. Our leading coefficient is greater than 0. Then we can say as x approaches negative infinity, y will also approach negative infinity. We can say as x approaches positive infinity, y approaches positive infinity. Okay, now the possible number of turning points. We have our degree. Our degree is 3. We determined already that the maximum number of turning points you can have is 1 less than the degree. So in this case, our maximum turning points is 2. Now we could also maybe have 1 or 0 turning points. I'm just using some shorthand here. Our degree is 3, so we could have 2, 1, or 0 turning points. Well, hang on. What happens if we have just 1 turning point? I'm just going to give myself a therefore. Therefore, this number of turning points. So let's just visualize here. If a function has 2 turning points, it might look like this, right? Turn, turn, in which case it has opposite end behaviors. So that's 2 turning points. But then let's take a look. Let's consider if our function has only 1 turning point, it would have to look something like this. Or it could look something like this. But either way, its end behaviors would be going in the same direction. That's not what's going on here. And we know that because our degree is odd, therefore it cannot possibly have exactly 1 turning point. But if we go back into it and we check out 0 turning points, that's like a constant function. Again, it does have the end behaviors in opposite directions. That's certainly allowed, so we can have 2 or 0 turning points. We cannot have exactly 1 turning point here. Now the possible number of zeros, again, if it is an odd function, then it must have at least 1 0 because its end behaviors are in opposite directions, right? Whoops. There we are, because its end behaviors are in opposite directions, so it must have at least 1 0. The maximum number of zeros would be the degree of our function. So the possible number of zeros would be 3, 2, or 1, or 1 0. Example 3, what could the graph of a polynomial function with a certain range? Okay, so we're told the range that we must be working with here, and 3 turning points look like. And you know what, at this point, I will say you should be able to handle something like this on your own. Try it out, see what it looks like. The answer will be posted on the Brightspace Classroom. Same thing with examples 4 and 5. Try them out. If you're not able to get anywhere, that's okay. We will at least share our answers or share where we got stuck when we get into class next.